Everybody. Today we will be taking a look at lesson 2. We are going to be taking a look at pH scales today. The learning goals for today are to understand the relationship between pH and hydronium concentration, and that POH and hydroxide concentration relationship is logarithmic. We're going to learn how to measure acidity and basicness or basicity on a pH and POH scale. Understand the relationship of how hydronium, pH, hydroxide, and POH relate to each other. For today's review, we're going to be taking a look at logarithmics. Essentially, logarithmics, or logs for short, are an answer to the question 10 to the power of what equals. So basically, we're going to take a look at these two problems here. So basically, a log tells you how many times a number multiplies by itself. So if this was to the power of 1, it would be 10 times it once. It would just be 10. If this was to the power of 2, it would be 10 times 10. So what is the power of x to get 100? Well, you would have to multiply 10 times 10 to give you 100. So essentially, it would be 10 to the power of 2. So therefore, x is equal to 2. Same thing here. What is the power of x if 10 to the power of x equals 1,000? So in this case, you are actually going to have 3 of them multiplied together. So 10 times 10 times 10, which is the same thing as saying 10 to the power of 3. Therefore, x is equal to 3. So on a pH scale, we increase and decrease by factors of 10. Let's go down and kind of explain that to you. So here I've drawn a pH scale 1 to 14. Let's first of all look at what a pH scale means. Down here, from 1 to 7, we are in acidic region. 7 is considered neutral, and between 7 and 14, we're considered to be in basic nature. Basically, so if we're increasing this way, if we are going this way, the term could be used as we're becoming more basic or less acidic. Okay. On the contrary, if we are going from this side towards 1, we are becoming more acidic or less basic. So let's kind of look at how to work this pH scale. Going down here, we have some examples. The first one says a pH of 1 is blank times more acidic than the pH of 2. So we are comparing it to 2. I'm going to draw a pH scale down here. 1, that is definitely not the number 1. 1, 2, 3. So I'm just going to take this little snippet of the pH scale. So 1 is our end goal because that's what we're comparing it to. We're comparing it to 2. So to get to 1 to 2, it would be 10 times more acidic. Because again, when we're approaching 1, we are more acidic. So this would be 10 times more acidic. Okay, let's look at the next one. pH of 10 is blank less acidic than a pH of 7. So I'm going to draw a little segment of our pH scale here again. Let's start it from 7, 8, 9, 10. I'll use a different color this time so you guys can see it. We're going to start with 7 and get to our end goal. So 7. It moves once, that's times 10. If it moves again, it's times by another 10. If it moves again, it's times by another 10. So in our overarching, it's times by 1,000, because 10 times 10 times 10 gives us 1,000. If we are headed towards 14, we are becoming less acidic. Okay, so this is 1,000 times less acidic than a pH of 7. Okay, so last one, pH of 11 is blank acidic than pH of 9. So again, let's start off by drawing a little segment. Okay, 9, 10, 11. Let's use a different color so you guys can see what I'm doing here. We're going from 9 to 11. That's times 10. It's times 10. Overarching 10 times 10 is multiplied by 100. Okay, so it's 100 times. Now we're approaching 14, so that's going to be less acidic. Scroll this down a bit. So the word here, less acidic. Okay, so now here I have a pH scale, and now I've introduced hydronium concentration up here. So this is the concentration of hydronium. We'll write that in here, H3O+. You're going to notice that the concentration of hydronium is related to the pH number. So if we have 1 times 10 to the negative 1, that's a pH of 1. 1 times 10 to the negative 7, that's a pH of 7. 1 times 10 to the negative 14, that's a pH of 14, okay? Now, if our hydronium concentration is less than 7, okay, so let's take a look at this concentration. When your hydronium concentration is greater than 1 times 10 to the negative 7, it is going to be considered acidic. Okay, so it's going to be in this region here. Now, I know this may be a little bit harder to memorize with the hydronium ion. So if it helps, if you know the pH ranges, you should be good. Now, if your hydronium concentration is less than 1 times 10 to the negative 7, then it's going to be considered basic. So it's going to lie in this region here. Lastly, if your hydronium concentration is equal to 1 times 10 to the negative 7, then we are going to be in neutral region. So right here, this will be considered neutral. Basically, in a solution, the more hydronium ions, the higher the concentration of hydronium ions in a solution, the more acidic it's going to be. As that hydronium gets diluted out, it's going to become more and more basic. Okay, so let's fill in the statement here. As pH increases, so as pH increases, gets more basic, the concentration of hydronium ions decreases. Okay, it's backwards. So remember, pH, bigger number, if it's in 14, above 7 to 14, it's considered basic. So as we move towards 14, our pH increases. Our pH increases because our hydronium concentration is decreasing. 1 times 10 to the negative 14 is a lot of zeros before we see a number. Okay? Okay, significant digits. So we're going to learn some new math rules for significant digits using pH. for pH, the significant digits are on the left of the decimal are considered significant. So for pH, the digits on the left are considered significant. So what I mean when I say that the digits on the left of the decimal are considered significant when it comes to pH, this is what I mean. Say we have our answer 2.02. We are only looking at these digits here to be considered our significant digits. So this number would have actually 2 significant digits. This is only a rule that applies to pH and POH. We'll get into what POH is just a little bit later. The next one we have is 12.3. This number only has 1 digit to the left of the decimal, so it only has 1 significant digit. Okay, so let's introduce some formulas to you guys to help us fill in this table. First of all, if you are calculating hydronium concentration from pH, the formula looks like this. So to find your hydronium concentration, you're going to go 10 to the power of negative pH. So let's just go ahead and take a look at example 1 here. If I were to be using example 1, I would go 10 to the power of negative 5.94. So let me grab my calculator. Okay, so in our calculator, we're going 10. If you have the newer version, you won't have to use brackets when you press the exponent button there. So that little hat is the exponent button. I'm going to use brackets because this is the older version. Negative 5.94. Close the bracket. And there is your hydronium concentration. Now, it's really important that we report our answers to the correct significant digits. So in this here, we have 2 significant digits, okay? And the answer that we got from our calculator was 1.148 ... times 10 to the negative 6 moles per liter. Okay, hydronium concentration is always measured in moles per liter. So if we have 2 significant digits, we're going to report our hydronium to 2 significant digits. Now, the hydronium concentration and the hydroxide concentration will use our regular significant digit rules. So we need 2 digits. I'm going to get 1.1 times 10 to the negative 6 moles per liter. Okay, let's work backwards now. So we have hydronium and we want to work to find pH. pH is equal to negative log of our hydronium concentration. I'll use a different color here. So let's say we're plugging in this number. Negative log, bracket, 2 times 10 to the negative 8. So let's go into our calculator. Negative log is right here. Negative log bracket 1.10. Now times 10. Okay, that's represented by this E right here. To get that E, you're going to press second, E, negative 8. So this is saying times 10 to the negative 8. Close that bracket, enter. We get a pH of 7.677. Okay, so looking here, how many significant digits do we have? Here we have 3. Remember, hydronium uses regular significant digit rules, and pH uses the special. So if we have 3, we're going to report our answer to 7.678. Okay, let's go ahead and identify the nature of our solution. If we have a pH less than 7, it is going to be an acid. If we have a pH greater than 7, it is going to be a base. Okay, I'm going to give you some time to try the problems on the bottom by yourself, and when you are done, you can unpause to check your answers. Okay, here we are. So for the first one, I used this formula here. Once I plugged everything in, I got an answer of 5 times 10 to the negative 15. This has one significant digit. This has one significant digit. For the second one, oh, and it is basic because it is above 7. Yes, you can go above 14 on the pH scale, and you can go below 1 on the pH scale as well. There are negative pHs as well. Okay, so now let's say here it's 1, so it's less than 7, makes it acid. This has 3 significant digits, so we will report 3 significant digits for our hydronium concentration as well. Fun stuff. Okay, so let's move on to word problems. Well, simple word problems. A glass of orange juice has a hydronium concentration of 3.7 times 10 to the negative 3. Now, it's asking us what is the nature of the solution. Is it acidic or basic? So if we go back up to our original chart here, we'll notice if the concentration is greater than 1 times 10 to the negative 7, it's going to be acidic, okay? So we have something that's in the times 10 to the negative 3 region, so we should be getting a pH around 3 when we put that calculation in. So I'm going to say that this is acidic. Now let's test that out. Let's see if we actually get a pH around 3. So to find pH, you're going to go negative log of your hydronium concentration, which is equal to negative log of 3.7 times 10 to the negative 3. When you plug that into your calculator, you're going to get an answer of pH is equal to 2.43. There are 2 significant digits here. There are 2 significant digits here. This is my final answer. You will still round the same, but in a pH or POH situation, you will only report decimal numbers that are significant. All right, this question I'm going to have you try on your own. When you're ready, you can unpause and check your answer. Here's the answer that I get. You use the formula, not that formula, you use hydronium is equal to 10 to the negative pH. When you plug that in, this only has 1 significant digit, so I will report my concentration to 1 significant digit. All right, let's move on to the POH scale. What does POH? So if we're measuring acidity and the hydronium concentration on the pH scale, we're measuring basicity and hydroxide concentration on the POH scale. So in honor of the basic side of the POH scale, we will say we'll use blue. So we're measuring basicity, and the POH scale is basically opposite to the pH scale. So, oh boy, my lines are not equal. So let's say we have 7, 1, 14 here, and then 1, 7, 14 on the POH scale. Let's first identify our acidic side on the pH scale. It lies between here, so this would be our acidic region on the pH scale. The acidic region on the POH scale is 7 to 14. All right. Basic region between 7 and 14. You are basic on the pH scale. If you are basic on the POH scale, it's between 1 and 7. So it's basically flipped. To be neutral, you have to be exactly 7. on the pH scale and exactly 7 on the POH scale. Neutral. So now, what is the relationship between those two scales? Let's go find out. Here I have some data. What do you notice about the pH number and the POH number if you add them together? Let's take a look at the first one here. If we add our pH number plus our POH number, what number do we get? So our pH number is negative 0.65 plus 14.65. Oh, hey, we get 14. Let's test that out with one more. Let's take this one on the bottom here. We have 13.92 plus 0.079. 13.92 plus 0.079. We get 13.999, which rounds to 14.00. So when you add your pH and your POH together, you get 14. That is the relationship between the two. Let's go back to this diagram here just for a minute. Oh, wrong one. Scroll down. So let's say we have something here laying in the acidic region. Let's say we have something with a pH of 3. So we know if our pH and our POH add together, so if pH is equal to 3, our POH is equal to 14 minus pH, which is equal to 14 minus 3, which is equal to 11. 11 is about here. They both lie in the acidic region. It doesn't matter if you represent it as pH, it doesn't matter if you represent it as POH. It is still considered acidic on both scales. Okay, so lots of formulas to introduce to you guys now. So the relationship between pH and POH. Okay, so, sorry, pH and POH. pH plus POH is equal to 14. The relationship between pH and hydronium ion, sorry, we're not going to do this. These are the two formulas. pH is equal to negative log of your hydronium or hydrogen ion concentration, and hydronium is equal to 10 to the negative pH. One more set of formulas here for you. POH is equal to negative log of your hydroxide concentration, and your hydroxide concentration is equal to your negative 10 to the power of negative POH. I'm going to make you a flow chart because sometimes you're going to be asked to calculate everything. Example A here. So we're going to make a beautiful flow chart here. This is how your flow chart will always be set up. Hydronium, pH, POH, and hydroxide concentration. Okay, to go from hydroxide to pH, you are going pH is equal to negative log of your hydronium concentration. To go from pH to POH, I am going to, okay. Okay, so to go from pH to POH, it's POH minus 14. And then lastly, to go from POH to hydroxide concentration, you are going to go, hydroxide is equal to 10 times 10 to the power of negative POH. If you're going the other way, let's use a different color here. To go from hydroxide to POH, you are going POH is equal to negative log of your hydroxide concentration. So sometimes you will get hydroxide concentration and need to work your way all the way to hydronium. To get pH, you are going pH is equal to 14 minus POH to go that way. And lastly, to come back here, you are going to go hydronium is equal to 10 to the power of negative pH. What about this connection here? Don't worry about this connection. It is something that you will learn in Chem 30. There's actually a whole unit dedicated to it. So don't worry about this for now. We are just going to take the long way. This is Chem 30. Okay, we're going to put our beautiful flow chart to work here. Example 4 is asking us, what is the hydroxide concentration of a solution that has 9.09 times 10 to the negative 3 molar concentration of hydronium? Okay, here's what we're going to do. We're going to start with what we know. This is a very common trend that I have been talking about in Chem 20. You always start with what you know. So I have my hydronium concentration. It is equal to 9.09 times 10 to the negative 3. Okay, we got to convert this guy into pH because we need to get all the way down here to our hydroxide concentration. That's what we're looking for. So to turn this into pH, you are going to go pH is equal to negative log of 9.09 times 10 to the negative 3. That's going to give me a pH of 2.04 times 10 to the negative 8. Okay? Oh, not times 10 to the negative 8. 1 second. Just 2.04. Okay, dot, dot, dot. We're not rounding yet because it is an intermediate step, so I will show that to you at the end. Then we have to change this into POH. POH is equal to 14 minus pH, 2.04, which gives me a POH of 11.96. Now we have to change this into hydroxide. So we get OH minus is equal to 10 to the power of negative POH, which gives me 1.10 times 10 to the negative 12 moles per liter. Let's review this. I'm going to get a highlighter out. Start with this. We use it. It gives us pH. Then we use pH, and it gives us POH. We use POH, and that gives us our final hydroxide answer. I'm going to walk this one through once with the calculator with you, and then Yeah, that'll make some more sense. So we're going to go negative log 9.09. Remember, E represents 10 to the power of negative 3. Enter. There it is, 2.4. Then we convert that into POH. So I go 14 minus answer. So I click second, answer. Oh, look, there it is, our POH. 11.958. Then you're going to take that and convert it into your hydroxide. 10 to the power. Now my calculator is old, so I have to go negative, answer, enter. There it is, 1.10 times 10 to the negative 12. Okay, here I have a table for you. I'm going to do the first one with you using this POH, and then the rest I will fill in and you guys can check your answer. So let's extend the page. Okay, so the first section of that table said that the POH was 7.69. So if I'm looking on my thing, 7.69, this is my POH. It's my starting. We need to find everything else. So let's go ahead and find our hydroxide concentration first. So I'm going negative, hydroxide is equal to negative log of my POH. So 7.69. My hydroxide ends up being 2.0 times 10 to the negative 8. I am rounding all my numbers now because they are being used for in the table. So I'll fill that in. 2.0 10 to the negative 8. Perfect. Let's work our way down. So now from here I can go up and find pH. So let's go ahead and find pH. pH is equal to 14 minus 7.69, which will give me an answer of my pH, which will be 6.31. Now I can take that and find hydroxide. Hydroxide is equal to 10 to the negative of our pH, which is 6.31. Plug that in. You are going to get your hydronium concentration to be 4.9 times 10 to the negative 7. Let's go ahead and fill that in. Our hydronium was 4.9 times 10 to the negative 7, and our pH is 6.31. Okay, so here you can pause, and when you're done, you can come back and fill in the table and check your answers. Okay, you guys can go ahead and check your answers here. If you do have any questions, please email or forward us your questions. Okay, this is the end of our lesson. This is a trickier one. I do recommend that you do your homework today. So we will see you in the next lesson. This lesson 2 is so important for the next lesson. If you do not understand this lesson, you guys do need to reach out and email us.